Anyway, Edward Witten would take 1,000 of Wormholes.
Well, when I was asked, thank you, Natty, and thanks for the invitation. When I was asked to give this talk, I wanted to pick a topic that might be interesting for the condensed matter audience, and also a topic where the answers aren't known, so there might be an opportunity to contribute. There is a drawback with the topic, which is I have to accept the fact that there are people in the audience who know much more about it than I do, so I have to be a little bit thick-skinned in giving this talk. So what is a wormhole? A wormhole is a localized connection between two different universes or a shortcut between two different regions in one universe. So I've drawn the two pictures. A is a shortcut, is a connection between two different universes, but in B, two potentially very distant regions in the same universe are connected by a shortcut. But there are two completely different things we could mean, because that picture I drew is fundamentally ambiguous. We could have in mind wormholes in space or wormholes in space-time. So in one case, this is the two pictures, either A or B, is a snapshot of what there is at a given time. And if you include a time, it would evolve and maybe the wormhole would move around or something or change in size. And the other case is the wormhole is localized in space-time. Time is included in the picture. The first case of a wormhole in space is relatively well understood, and the second case is not. Of course, both pictures involve curved space-times, so they're mainly relevant in theories that include gravity, which will be implicit throughout the talk. Well, the simplest example of a wormhole in space arises if we take a spherically symmetric black hole and extend the space-time beyond the horizon. This was actually first done by Einstein and Rosen in 1935. Long before the full picture that I'll explain in a little while was understood. So I've written the metric for a spherically symmetric black hole of mass m, where d omega squared is the metric of a round two-sphere of unit radius. But we're going to look at this at time zero. So we forget the time and just look at a spatial metric at time zero, which will be this one. And we observe that the coordinate system used here is not a good coordinate system because the metric has a singularity at r equals 0, at r equals 2 gm. So for the moment, we'll only consider the region where r is bigger than 2 gm. Well, what does this metric describe? Well, it's a three-dimensional metric, of course, but it's spherically symmetric. So it's like a three-dimensional version of a surface of revolution. But the size of the spheres is variable. The size has radius, the sphere has radius r because of this r squared factor, where r is one of the coordinates. So a picture of what it looks like would be something like this. So at large r, you just would have r3, because this coefficient becomes 1, and we just have dr squared plus r squared d omega squared, which is r3 in polar coordinates. But when r becomes small, the metric is distorted, and it looks something like what I've drawn. R equals 2 gm is at this circle, well, it's actually a two-sphere, but in the picture it's drawn as a circle at the bottom. So a tube comes out of the, well, if you were embedding this geometry in 4 dimensions, you would do it as I've drawn. You'd have a flat R3 embedded in R4, but then a tube comes out, and the tube ends at a finite distance at R equals 2 gm. Anyway, the geometry is roughly a three-dimensional version of the two-dimensional surface that I've drawn. But Einstein and Rosen realized they could make a smooth manifold without boundary by gluing together two copies of what we just described. You take what I had and then you glue on a mirror image down below, and you include the points at r equals 2 gm, which now are this circle, which is in blue, but the blue color is probably hard to see. And you make a smooth manifold without boundary. The smooth gluing relies upon the fact that, as Einstein and Rosen noticed, r is not a good coordinate where r equals 2 gm because of this singularity in the metric. They introduced a better coordinate u by this formula, and that eliminates the apparent singularity at r equals 2 gm. And actually, I just took this formula from their paper. It's completely smooth, provided we let u go from minus infinity to plus infinity. The equation u squared equals r minus 2 gm has two roots, with positive or negative U. And let's say positive U corresponds to the region we started with, and negative U is the second copy that they glued on. And the two pieces can join smoothly at R equals 2gm because, as you can see from the definition of U, dr du is 0 at R equals 2gm, which ensures that the two pieces join nicely. Now, all this discussion was at time 0, so we found that at time 0, the extended black hole solution has a wormhole connecting two universes. As we let it evolve in time, the wormhole doesn't go away. It actually evolves dynamically. And, well, first of all, it took about another 25 years before this full space-time picture was understood by Kruskal, Sakaras, and others. And it's most efficiently described in a Penrose diagram, which some of you will be familiar with. I want to explain it a little bit in case you're not, although it's a little hard to explain it briefly. In the drawing the diagram, spherical symmetry is assumed, and only two dimensions are shown, which roughly are time going vertically and space running horizontally. Crudely, you could think of the left to right coordinate as that coordinate u of of Einstein and Rosen, where u equals infinity at this left edge, and u is minus infinity here and plus infinity here. And there's a future black hole singularity and a past black hole singularity. The two diamonds are the regions. The region at R equals 2gm is in this diamond, and this diamond is the second region that Einstein and Rosen had to glue in, extended in time. And the important thing about the picture, well, first of all, following Penrose and drawing the diagram, first of all, we make a conformal mapping so it all fits in a finite picture. So infinity, like u equals infinity or minus infinity, all infinities have been moved to a finite distance in the picture. But it's done in such a way that a light ray that's going in or out is at a pi/4 angle from the vertical. And any causal curve is at most at a pi/4 angle from the vertical. So to an observer who lives in this region, this diagonal line is a horizon. Causal signals travel at most at a pi/4 angle to the vertical. So if you're in this diamond, you can't see what's behind the horizon. That's why it's a black hole. Of course, the horizon aspect was not understood by Einstein and Rosen, who worked purely at time 0. So they did not have this picture. Now, for quite a while after Kruskal and Sakaras as assisted by Penrose, drew this picture, the meaning of the second asymptotically flat region wasn't understood. It was understood in the 70s when black hole thermodynamics was developed by Bekenstein, Hawking, Gibbons, and others. So a black hole has a thermal interpretation of the Hawking temperature, which for a spherically symmetric black hole is given by this formula here. Now, in general, of course, a thermal density matrix is not a pure state. It's a quantum mixed state. But a mixed state can be purified by adding a second copy of the original state. And in the case of a thermal density matrix, that purification gives what's called the thermophile double state, where you sum over all energy eigenstates of the original system, but you add a corresponding state of a second copy, and then you weight them with the square root of the usual thermal factor and 1 over the square root of z. And that gives a pure state for which the associated one-sided density matrix is thermal. So what was understood in 1976 was that in the case of a spherically symmetric black hole, you could study this quantum system at any temperature, but if you take the black hole at the Hawking temperature, then its thermophile double state is actually a simple state of the quantum fields in the doubled spacetime. So more briefly, when you see the Penrose diagram, the black hole exterior, let's say, might be this diamond, but the thermophile double state of the quantum fields in this region are described by adding a second identical region behind the horizon. So the two copies correspond to the two copies in the thermofield double state. Well, in a general quantum system that's entangled, what does entanglement between the two copies mean? It's some kind of postponing that for a second. In general, we could consider quantum entanglement between the two copies in the thermofield double, but the black hole has the mysterious property that entanglement is manifested in a geometrical connection between the two copies. So abstractly, the thermofield double state, you'd say the two copies are entangled, but in the case of the black hole at the Hawking temperature, they actually are connected geometrically. Now, a basic test of the viability of this analogy between entanglement in the quantum case and a geometrical connection for the black hole is the following. In general, quantum mechanically, if you have a bipartite system AB with an entangled quantum state, measurements of system A are correlated with measurements of system B, but access to one system does not enable you to communicate with someone who has access to the other system. That's why the Einstein-Podolsky-Rosen phenomenon, which they wanted to present as a paradox, is regarded by modern physicists as a phenomenon rather than a paradox. The analog for the black hole is the following. The two copies of the black hole interior are connected geometrically, but it's not possible to communicate from one to the other. If you try, a message you send ends up at the black hole singularity. I've indicated that by this picture here. An observer in the left half of the space-time is sending a signal which possibly originates at this point in space-time. The signal at most can propagate at a pi/4 angle from the vertical. So therefore, the best you can do to try to communicate with this region is to send the signal at an ingoing null geodesic, which would be at a pi/4 angle, but it ends up at the black hole singularity, never reaching the other side. So that's how the geometrical picture of the geometrical connection between the two sides reproduces what we know in general from quantum entanglement. Now, I've drawn the picture for the ideal case of a spherically symmetric black hole, but there's actually a nice theorem in classical general relativity says this is always the situation. The theorem goes by the name topological censorship. Spatial wormholes, connections between two different regions in space, between two different spaces or shortcuts between two different regions of space, can exist in general relativity, as we see from the black hole solution. But it's never possible to travel or to send a signal through the wormhole. So they called it topological censorship because although space can have a non-trivial topology, you can't observe it. The attempt to travel through the wormhole or to send a signal through the wormhole always comes to a bad end, as it does in the case of the Schwarzschild geometry. The proof is not too hard, and given a little more time, I would explain it, but I think I'll have to skip it today. I actually wrote some lecture notes on general relativity a few years ago where you could find my version of the proof if you're interested, and I think you'll find it's simple. So, okay, that's what I will tell you about wormholes in space. And up to a certain point, wormholes in space are relatively well understood. At least in the case of the black hole, the relation between geometry and entanglement is satisfactory. It's suspected that there's a wide generalization, though this is certainly not really understood. One vision goes by the name ER equals EPR, meaning that quantum entanglement between two systems, symbolized by the Einstein, Podolsky, and Rosen phenomenon, which they regarded as a paradox, always corresponds to some sort of geometrical connection between the two systems, symbolized by the Einstein-Rosen wormhole that we've been discussing, also dating to 1935. Now, it's puzzling what this could possibly mean for a strongly quantum system like a pair of spin 1/2 particles that are entangled. All one can say now is that the geometrical connection, if it exists, is highly quantum in some sense we can't elucidate. But anyway, even though we don't know what the general story is, this picture about wormholes in space is comparatively satisfactory. Now we're going to switch gears and discuss wormholes in space-time as opposed to wormholes in space. And there, what I can tell you is much less satisfactory. Well, the picture is the same, but the meaning of the picture is completely different. Because now it's meant to be a picture of space-time, not just a picture of space. And the wormhole is meant to be localized in space-time, not just in space. And with this interpretation, the picture does not quite work in Lorentz signature, at least not if we want a completely smooth space-time metric that everywhere has Lorentz signature. Intuitively, that's because there'd be a problem with the flow of time. How could time flow in such a picture? The flow of time would have stagnation points somewhere inside the wormhole, or more technically, a time function would have critical points. So these don't exist as completely smooth metrics that are Lorentz signature everywhere. They can exist as smooth metrics that are Lorentz signature except at exceptional points. But anyway, partly because of this problem with Lorentz signature, the modern study of wormholes really started in Euclidean signature. I'll explain at the end that that's not the whole story, but anyway. Gibbons and Hawking had shown in the 70s, originally again involving black hole thermodynamics, that Euclidean signature path integrals are a powerful approach to quantum gravity, at least for some purposes. So the study of space-time wormholes started out in Euclidean signature. Now, in part A of this picture, where we're connecting two different regions, one usually tries to find a wormhole as an exact solution of general relativity coupled to some reasonable matter system. By the way, you can prove that such solutions do not exist in pure general relativity. So they do require support by a suitable matter system. And one expects that, or hopes that the wormhole will turn out to have some definite size and shape determined by the equations. Such solutions are a bit scarce in asymptotically flat worlds, but there are some examples found by Giddings and Strominger originally. In case B, it's too much to hope for an exact solution, because if the wormhole ends if the wormhole is a shortcut between two distant regions of the same universe, even if the regions are distant, you'd expect that the ends would attract each other or repel each other at least exponentially, at least with an exponentially small effect. So one doesn't expect an exact solution, but one expects a very good approximation if the two ends are very far apart compared to the size of the entrance or mouth of the wormhole. Literally, if you take an exact solution in A, you can modify it to make a very nearly exact solution in B, assuming that the two ends of the wormhole are asymptotically far apart. In A, the two ends of the wormhole can be attached anywhere. In B, that's true as long as they're sufficiently far apart. Now, the question Coleman addressed was, what sort of effective action is produced by a wormhole? Well, before reviewing his argument, let's think for a moment about instantons, by which I mean, for example, a classical solution in Euclidean space Rn. And I've just drawn the instanton as a purple blob without worrying about what it's made out of. Now, the interpretation of instantons is more straightforward if we can assume the instanton has a definite size, or at least a maximum size. For example, in particle physics, this assumption is valid for weak interaction instantons, but not for instantons in strong interactions. If the instanton has a definite size, then seen from far away, it just looks like a local interaction. So, but we have to integrate over the position of the instanton, of course. So the instanton from a big distance can be replaced by some local operator integrated over space. The O's run over all, in principle, all local operators of the theory, maybe with some constraints due to symmetries and anomalies, and the C's are C-number coefficients. In practice, of course, one would expect that the important contributions would come from one or at most a few operators of low dimension. So that's instantons. Well, by analogy, you see, wormholes would seemingly be similar, except that we have to integrate over the positions of the two mouths. And that would appear to produce a bilocal action. I've treated the two mouths as identical bosons, so I gave a factor of a half, but otherwise we integrate over x and y, and we have a bilocal interaction. If you're far away from both mouths, it looks like there's an operator OI at the end x, but also an operator, oh, this I, second I should be a j, an operator OJ at the end y with some C number coefficients. So the wormhole would appear to produce a bilocal action. But are bilocal actions physically sensible? Well, Coleman, instead of giving up on macroscopic locality, proposed an alternative interpretation in which the constants of nature are random variables. So to understand the proposal, schematically consider the action function of the universe with operators OI and coupling constants Fi. And then, so the functional integral is an integral over some fields which I'll call phi alpha of the exponential of minus I times the action. But Coleman modifies this by treating the f's as random variables. Suppose, for example, that the f's are Gaussian random variables with a simple Gaussian measure. Well, now we'd be integrating not only over the fields phi alpha, but over the random variables Fi, the coupling constants. And what we're integrating is what it was before, the exponential of minus the usual action, times a Gaussian measure for the couplings. Well, we can do the Gaussian integral over the f's first, and of course, well, what that produces is precisely a bilocal action. Integrating over the f's will give a Gaussian function of the o's. So it gives something like what wormholes appear to give. So Coleman's argument was that averaging over the values of random couplings gives us precisely the sort of bilocal action that we appear to get from wormholes. There's no reason that one would not expect in this philosophy that the measure for the coupling constants is exactly Gaussian. We got that because we considered a wormhole with precisely 2 ends. If there's a wormhole solution with 3 ends, and I must tell you that in asymptotically flat worlds, there are no known examples that are reasonable. But anyway, if we had such a solution, we'd get a trilocal action in spacetime. And to reproduce it, we'd need to assume a cubic term in the measure for the coupling constants. And so on. Well, a question you could ask is whether it's important that the wormhole exists as a classical solution. Might not it be enough to just have wormhole field configurations on the grounds that integrating over field configurations, even if they're off-shell, gives something which would be bilocal and lead to the same outcome? Well, the answer to this question is maybe, because well, in theories with gravity, it's not clear in general how far we can push the Euclidean path integral, and to what extent it makes sense beyond expansions around classical solutions. So we don't have a clear answer to the question I asked at the top of this page. But a pragmatic answer is that when there's a classical solution to expand around, we can do that and compute answers. When there isn't a classical solution, we can just contemplate what to do, but we can't do anything concrete, usually. Now, back in 1988, there were various possible reactions to Coleman's work. Some didn't like the idea of thinking of the constants of nature as random variables. Some liked it more. But whether you liked it or not, there was no clear alternative in a theory with wormholes to Coleman's suggestion, and no clear internal contradiction in his picture. There was some tension between Coleman's proposal and string theory. String theory appears to give us quantum gravity theories that do not depend on any coupling constants that could be treated as random variables. These are theories with 0 cosmological constant. It's actually, wormholes and theories with 0 cosmological constant are scarce, and the original examples of Giddings and Strominger, with some slight bells and whistles added, are still today the only examples known. However, it's been claimed that examples of this type can be embedded in string theory, though sometimes these embeddings lead to instabilities. So anyway, this is one problem. The tension became sharper with the discovery of duality between anti-de Sitter space and conformal field theory in 1997. Here, there were many examples of quantum gravity theories in worlds with negative cosmological constant, and it turns out that this makes it much easier to construct wormhole solutions, including solutions with any number of n's. 2n's, 3n's, any number. So examples were explored in this paper. In many known examples of the duality, it's believed with high confidence, though not as a true mathematical theorem, that the CFT depends only on a small number of known parameters, in some cases only a single integer n, and it does not appear that this provides a sufficient framework for Kalman-style averaging. So this has been a puzzle. We can make the puzzle more concrete as follows. Suppose we have a CFT and we want to calculate its partition function on a closed D-manifold M. In ADS-CFT duality, the gravitational recipe is to sum over all bulk manifolds X of one dimension more, such that M is the boundary of X, not of M, in the conformal sense. It should say that M is the conformal boundary of X, as drawn in the picture. For each X, we do a path integral over the fields on X, and then summing over X, that's supposed to give the CFT partition function on M. The problem arises if M is the disjoint union of, say, two components M1 and M2. In CFT, the partition function on two unconnected manifolds is just a product of the separate partition functions on each one. And as long as we consider disconnected manifolds X that have two components where X1 has boundary M1 and X2 has boundary M2, there's no problem. Summing independently over X1 and X2 will give the expected factorization of the partition function. The problem arises for connected manifolds X, whose boundary is the disconnected union of M1 and M2. You see that such an X is a wormhole in a generalized sense, because it connects two asymptotic worlds, M1 and M2. And with negative cosmological constant, wormholes are basically much easier to find. Such an X will contribute to what you'd like to call the partition function of the disjoint union of M1 and M2 in a way that cannot be factorized in any evident way as a product of contributions from the separate manifolds. So it seems to say that the partition function of M is not the product. The Kalman-style interpretation is that what gravity is computing in ADS-CFT duality is really the average of the CFT partition function over some random variables. So we think of all these partition functions as random variables, not just numbers as they conventionally are in CFT. Let's denote the average of the random variable Zm with a bar. So Zm bar is the average of Zm over some unspecified variables. Of course, if Zm1 and Zm2 are random variables, you expect that the expectation of the product is not the product of expectations. And this failure of factorization, according to the Kalman-style interpretation, is what we're getting from connected manifolds X. I've already explained what appears to be the problem with this interpretation. The relevant CFTs do not appear to depend upon parameters such that averaging over them can produce the observed effect. This is an unsolved problem, so I'm not going to be telling you an answer. Do I still have 5 minutes, Natty? Okay. So I will briefly mention an interesting but ultimately unsuccessful attempt that was made to get rid of the problem. Yao and I showed that if M1 and M2 have positive scalar curvature, a wormhole does not exist. Here I drew M1 and M2 as spheres, not round spheres, but anyway, spheres, to suggest that they have positive scalar curvature. In that case, a solution for X doesn't exist. That was interesting because it was also known that in examples of ADS-CFT duality where the CFT has a supersymmetric brane that can wrap on the boundary, the CFT is unstable unless the boundary has positive scalar curvature. So in examples of the duality with this property, Yao and I showed that whenever the CFT partition function is well-defined, the wormhole doesn't exist. So that was our attempt to get rid of the problem. but it failed for at least two reasons. Well, one is that although the most obvious examples of the duality do have the relevant supersymmetric branes, some examples don't. Although it is a curious fact that those examples behave strangely when M does not have positive scalar curvature. That's a fact whose significance hasn't really been addressed. But probably more importantly, our discussion assumed the wormhole solution is real in Euclidean signature, but contemporary applications of wormholes actually often involve complex geometries. I will conclude by a couple words about that, but I don't have time for too much. So I'll just very briefly mention a beautiful example involving a complex geometry, originally studied by Saad, Schenker, and Stanford. This involved a comparison of black hole physics to random matrix theory. In random matrix theory, if you have a Hamiltonian H treated as a random matrix, then of course functions of H, such as this trace of e to the minus beta H, except I gave beta an imaginary part corresponding to real time. Anyway, such functions are random variables. Random matrix theory makes a nice prediction for the large T behavior of averages, such as the absolute value squared of this random variable, equivalently the average of its product with its complex conjugate. Now, if we assume that the Hamiltonian of a black hole is completely non-integrable and pseudo-random, for which there was some evidence prior to this work in previous papers of the same authors and others, you might expect that the CFT partition function dual to a black hole would satisfy the random matrix prediction. And this is an example of, see, here we have the average of a product of two CFT partition functions. So to satisfy the random matrix prediction, the partition functions have to behave as random variables. So we need non-factorization. We need a wormhole. And they found a simple complex valued wormhole solution that does indeed generate the random matrix answer. So this is one simple example where it has been useful to consider complex wormholes. There isn't really time to explain the details, so I'll just say the solution is a quotient of a complexified version of the black hole geometry that we discussed at the beginning with that Penrose diagram. Now, this is by no means the only example of wormholes in current research, but it's what we have time for today. In conclusion, today I've described some things that work, or at least up to a point in the first part of the talk, and some things that don't work, or at least aren't understood. I hope I've at least entertained you, and since this is something we don't understand, we don't know where input might come from in understanding it better, so maybe some of you will offer some guidance. Thank you.
I was wondering, on the first part of the talk about the wormhole and the Einstein-Rosen bridge.
Yes.
Is it required, like, what is the connection between a wormhole and the solutions that you're connecting on black holes? Like, can it just be two non-singular solutions connected by a bridge? Where the radius just varies?
Well, are you asking what's the general definition of a wormhole?
Yeah, for example, and maybe it's unstable to the black hole.
Well, for wormholes in space, but what we mean by a wormhole is initial data for Einstein's equations that look like one of these two pictures. And then it would have, whatever it evolves, in general in physics, we can specify initial data, but the theory decides how it will evolve in time.
And the initial data is a black hole.
Well, here you can't tell from the initial data that it's a black hole, but in the case of the Einstein-Rosen bridge, its time evolution is such that when you solve for the time evolution, you learn it's a black hole.
But I'm asking, is there a solution?
The Einstein-Rosen bridge is an example of type A. You're asking if there are wormholes that do not evolve into black holes.
Exactly.
The topological censorship theorem that I stated more or less shows that I stated it, but I didn't give the proof. But I'm happy to tell you about my lecture notes in GR where you can read about the proof. But anyway, that theorem more or less shows that wormholes always evolve into black holes.
Thank you.
As seen from outside. Yes?
I was wondering, at the end of your talk, you showed the spectral form factors.
Yes.
which have short time, they have the parameter beta.
Yes.
So what is this beta and what is the rationale for calculating? We can certainly calculate them, but why?
Why not take beta 0, you mean?
Yes.
Well, you can take beta 0, but you have to be prepared for the fact that the CFT partition function, when beta 0, is not a function, it's a distribution, it's a function of t. So it's very singular to try to take beta to 0. But the logic here makes sense. You have to be prepared for some subtleties, but the logic makes sense when beta is 0. Beta is a kind of regulator that makes things a little bit smoother and mathematically simpler, but you don't need beta. Yes?
Yeah, so I wanted to ask about this ER is equal to EPR thing. So,
Yes?
normally, so nowadays, a way to think about the EPR paradox is we can measure, you have these values, right? And you can show that in these quantum systems, there's, distributions of measurement outcomes that are not possible in any classical system. So I just want to understand, with these wormholes, like, do you have, kind of qualitatively different classical probability distributions of correlations of outcomes between the two populations? That
Well,
mimic like a Bell's inequality?
the point of mentioning topological censorship was to explain why ER equals EPR is potentially viable. The geometrical connections that we get have the same property as quantum entanglement. They lead to correlated measurements, but not the possibility of communication.
So it really is a classical analog of like a Bell.
It's perhaps surprising, but by now it's been essentially known for a long time, since black hole thermodynamics, that geometry can mimic quantum entanglement. Yes?
Yeah, maybe slightly broader version of maybe the same question.
Speak up, please.
Sorry, I just have a related question to this. Is there something special about specifically the thermal states in this black hole thing that leads to connectivity of the two regions, or is it kind of expected a general entangled state will in this black hole context will have
Well,
geometry?
in the thermal case, you can find the exact solution. And in other cases, we expect qualitatively similar behavior, but exact solutions are generally not available. If you take a density matrix that's almost thermal, okay, to discuss this better, we should go through the Euclidean approach to black hole thermodynamics, which we didn't have time for. And then Gibbons and Hawking found a nice representation of a thermal density matrix. And that description makes it clear that there's a similar representation for any density matrix that's sufficiently close to being thermal. So it's not special to a thermal density matrix at all. Yes?
So some recent work has proposed the idea that by summing over wormholes or other similar solutions, you could restore factorization. Could you comment on that?
Well, I'd say it's mostly an aspiration. So personally, I presume that factorization ultimately is correct, but I'd say the mechanism is, beyond that, I can't tell you anything useful. And the attempts are interesting, but far from being definitive, I would say.
And we'll also take the point of view that the issues with averaging comes because Einstein gravity doesn't have all the information, that it's not a complete theory.
Up to a certain point, I think that must be, in case not everyone heard Sabir, what Sabir said was that implicit in describing the world by Einstein gravity, which is an approximation, might be some kind of fine coarse graining over a much finer structure that we don't know about. Up to a certain point, that must be part of the answer to the problem. But it's hard to see it as a complete answer because there's the sharp paradox of the CFT partition function, which in CFT should factorize. Gravity gives a non-factored contribution. And yes, in the large n limit, it gives a non-factored contribution, but the CFT partition function would be expected to factorize even in the large n limit. Well, there isn't anything that's been said that I would find entirely satisfactory. Are there any more questions?
Is it
absolutely clear that the ends of this wormhole cannot interact with non-exponential longer range forces?
In the space-time case? Okay, it's clear if we're in Euclidean signature. I might tell you that when we get to complex metrics, even though there are some useful results that have been found, general rules are not known. So I can only give you a general answer if we assume a Euclidean metric. For Euclidean metric, it's clear that there would be at most power law interaction, decaying power law interactions between the two ends. Because there'd be no interaction between them in case A, and the difference between case A and case B is only that a signal can go the long way around. And a signal going the long way around would decay, even if there are massless fields exchanging the signal. Signals going a big distance fall off at least as a power. What's that?
Power law decay.
A power law decay interaction between the wormhole ends is conceivable. Yes.
Time, so maybe you can ask this question, unless it's really urgent. We're already kind of. So let's thank Edward again.